Hello, everyone. Welcome to our course. Today, our invited speaker is Dr. MarciaZilli. She will introduce herself. Marcia, you can talk now.
Okay, hello everyone. I think most of you are good morning. So good morning for you guys. So I'm MarciaZilli. I am a postdoctoral researcher in the University of Oxford, but I am originally from Brazil. And today I'm going to talk a little bit about the South Atlantic Convergence Zone. So I don't know if Michelle, you have anything else to add?
No, you can go.
Okay, so before we start, just to let you guys know, as Michelle mentioned before, feel free to ask questions and interrupt me during the class. Feel free to do it verbally or to write in the chat. I will have my chat here on top. That's why I'm looking to the sky. You can ask in English, Portuguese, Spanish, however you feel more comfortable. If you do it in Spanish, please do it slowly because my Spanish is not great. Sorry about that. So with that, I will start sharing my screen. Which one I need to share? I believe it's this one. Let's see. There we go. I hope you guys can see my screen.
Yes, we can see.
Great. So as I mentioned before, I'm going to be talking about the South Atlantic Convergence Zone. So this has been my main topic of research for a lot of time now. So I hope I can convey a little bit of what I've learned so far with you guys. So this image that you have on this slide is a typical convergence zone, indicating like the disorganization of the cloudiness along this corridor of moisture. And it's usually bounded by dry air to the south. So we're going to understand a little bit more how this is formed and what's the importance of this for the South American climate. So these are the main topics I'm going to cover here. So a brief introduction of convergence zones in general. Also, then I'm going to talk about the importance to the climatology over South America and how the convergence zone is formed. We're going to briefly show a few examples of how we can identify the convergence zones, talk a little bit about variability trends in the future scenarios, and also some points that in my opinion at least, I think are challenges and topics, interesting topics for future research. So let's hope this video will work. Let's see. So this is, yeah, there we go. This is an animation of average precipitation over an entire year. Over the entire globe. This is from iMerge, and the yellows and blues are where you have precipitation. And what we can see is that, I'm going to repeat again, we can see this band of yellow forming not just over South America, but you can see it also over other continents and over the South Pacific, and how it fluctuates, or it pulses. Like now it's coming from the winter and it's starting spring and summer, and it starts to increase over the Southern Hemisphere. So this is just a still from that image where we can look at what happens in January. So this is the average of January precipitation over the Southern Hemisphere, over the entire globe, actually. And I'm going to highlight especially this area over the Southern Hemisphere. So this is more or less what we call the subtropics, so around 30 degrees south, maybe a little bit to the north, a little bit to the south of that. And on the classic idea of the general circulation, this should be an area of dry weather or dry climate. So this is the area where a lot of deserts are located. So in the Southern Hemisphere, we can think of the Western Australian desert, we can think of the Atacama Desert in Chile, and we can also think about Namibia Desert in Southern Africa. But at the same time, what we see here is these areas of very large precipitation, usually on the east part of the continent. And this is what we call the convergence zones. And that's kind of like their main importance because they are like one of the main systems to bring precipitation to this region of the Southern Hemisphere that it is usually drier. So the study of the convergence zones in the Southern Hemisphere started in the 60s with the first satellite images. And I'm just showing here 2 examples that I thought it was super cool. So these are 2 images from ESA satellite, where they would call photography at the time. And these are from 1967, from January on the left and from February on the right. So this is actually a mosaic of 15 days of images. And it's showing the South Atlantic conversion zone here, and also the South Indian conversion zone over Southern Africa. Same thing over the image on the right, so for the February image. So these bands of organized convection, as they call it at the time, were first noticed in the 60s. So if you go through the links here on the slides later, you can find these studies online. This is also quite cool. It's the first time that someone described where these conversion zones kind of like are located over the Southern Hemisphere. So this is from Stratton in 1973, where using the satellite images, he identified this kind of like regions of where these cloud bands occur more frequently over the South Atlantic, the South Indian Ocean, the South Pacific, and also something over Australia, although it's not very clear. Nowadays, we can use different types of tracking algorithms to identify these cloud bands, or different type of techniques. So this image here on the right is showing an OLR image from 1979, where we can identify the South Atlantic conversion zone over South America, the South Pacific conversion zone over South Pacific. I'm going to skip Australia, the South Indian conversion zone over Southern Africa. And in blue, we have the northwestern cloud bands over Australia, which it works a little bit differently from the other conversion zones, but some people also consider that a conversion zone. This image was done using an automatic tracking algorithm that I will talk a little bit more later. But if you're interested, they are compiled into a website that you can reach looking through that QR code there. We try to monitor this cloud bands like once per month and plot like the current situation of this cloud bands over the Southern Hemisphere. So talking specifically about the South Atlantic conversion zone, it is defined by the American Meteorological Society, defines this as a local maximum in cloudiness, precipitation, and a low-level convergence that occur from a northwest-southeast-oriented swath extending across southeastern Brazil and the western South Atlantic Ocean. And when we look at satellite images as the ones we saw before, we can clearly see this area of increased convection, so increased cloudiness. The image on the left is showing the water vapor image. The one in the middle is the visible channel, and the one on the right is the infrared channel enhanced. So you can clearly see first that, as I was mentioning, the convection is organized along this region. You can see areas of very intense precipitation with the darker blues here on the image on the right. And most importantly, it's not a cloud band, like a continuous cloud area, but it's an organization, an area where local convection is organized into a larger envelope. And this is what the South Atlantic conversion zone is. It's like the organization of the convection into a specific area in space and time. So again, looking at that image on the left-hand side, we see that the South Atlantic conversion zone can be seen as, if you look at the average precipitation over the entire year. So this is actually, on the left-hand side, we have the precipitation from iMerge over the entire iMerge measurement period until May 2023. And we can see that we have this maximum precipitation over southeastern Brazil. And when we look at December, January, and February, we also see this very clearly in this composites on the right-hand side from 2 different satellite data sets, so CHIRPS and iMerge. So the South Atlantic conversion zone is part of what forms the climate over the spring and summer season in Brazil. So it's part of the circulation and the precipitation there. So that's why it's so important to the climatology. Previous study identified that more than 50% of the precipitation in the South American monsoon system, or more than 50% of the precipitation in the tropical South America happens during the monsoon. And in some areas, more than 50% of the precipitation happens during cloud band events or during South Atlantic convergence zones. So for example, if you look at Eastern Brazil, I think more than 60% of the precipitation is caused by the occurrence of South Atlantic convergence zone. So besides being one of the main mechanisms to form or to cause precipitation over this region, it also can, it increases the probability of having extreme precipitation, especially over southeastern Brazil. So it's also a way to forecast or to infer that you might have extreme precipitation when you have a South Atlantic convergence zone. So this maps on the bottom right are emphasizing that depending on the location of this convergence zone, you can increase the intensity of your intense precipitation either over the countryside or the interior part, or central part of Brazil, or more over coastal areas, depending on where the convergence zone is formed. We're going to see this throughout the class. So in years where you have a lot of South Atlantic convergence zones or very intense events, you can have floods, landslides, and a lot of all these natural disasters. But on the other hand, years that you don't have enough convergence zones or below average convergence zones, you can have droughts. For example, what happened in 2014 and 15 in Brazil, the water crisis was due to the lack of convergence zones. So how these convergence zones are formed? One of the first paper to really comprehensive analyze the mechanisms to form this diagonal convergence zones over southern hemisphere specifically was Kodama in 1992, and he also has a follow-up paper in 1993. And he defined that the main ingredients for you to have a convergence zone is, number one, you have to have convection from the core, usually from the core of monsoony regions, and this extends eastward into the continent or into the ocean. So that's what we see over the Southern African monsoon system, the Australian monsoon, and the SACZ here over Australia, and South Pacific Ocean, and the core convection over the Amazon related to the South American monsoon system. Then on top of that, you also have to have convergence in lower levels, as the name say. And this convergence comes from two different sources. The first one comes from the fact that over the subtropics, your subtropical jet will have a trough, and on the east side of this trough, you're going to have the formation of the cloud band or the convergence zone. And this trough or the position of the subtropical jet also helps us bound the southernmost limit of the convergence zone, of the monsoon region. And on the tropical side, we usually have this cloud bands also forming on the west part of a subtropical high. So the subtropical highs usually are located over the ocean, and they advect moisture from the ocean into this convergence zone over the west part of the plate. So you have this poleward or northerly flow coming into the northern part or the equatorward side of the convergence zone. And on top of that, you also usually have easterly or northeasterly transport of moisture coming from the tropics or from the convection in the tropics. So these are the main ingredients for you to have a convergence zone. You have to have the northerly winds on the west boundary of a subtropical high, advecting moisture and energy into the area. You also have the trough on the subtropical jet, so bringing also the energy and the disturbance into this region. And then you have the easterly transport of moisture from tropical convection into the region. So this is more commonly, all these criteria are more commonly met when you have the South Pacific convergence zone and the South Atlantic convergence zone. It's less frequent, but still quite frequent over Southern Africa, or sometimes it forms over South Africa, sometimes it forms a little bit over Madagascar. So it's a little bit, the convergence there is not so strong, so these criteria are not met as frequently. And then over Australia, you eventually have this also, and they are called northwestern cloud bands, as I mentioned before, and they are quite important to bring precipitation, especially to southeastern Australia. Cool. So now talking specifically about the South Atlantic conversion zone, how this ingredients are formed over the continent. So in upper levels, what we have typically during the conversion zone is the Bolivian high, which is the high circulation that you have on the top of the Bolivian plateau. You also have usually the northeast low quite well formed. So you have this dipole of circulation on upper levels, and the subtropical jet, as I mentioned before. So the subtropical jet usually will have a trough over the continent, and on the east side of this trough, you're going to have the convergence forming. In lower levels, you also have the Chaco Low over the countryside in Argentina, or northwest Argentina, and southeastern South America. The presence of the low-level jet, usually this low-level jet's a little weaker than normal and advecting moisture to eastern Brazil. And the South Atlantic subtropical high will also be very important to form this, being the source of these northerly winds that we need to have inputting water vapor and energy into the conversion zone. So breaking down a little bit more into upper levels and lower levels. So in upper levels, this is on this map, I'm showing a composite during cloud band days or South Atlantic conversion zone days. The arrows are showing the winds, and the shades are the anomaly in the zonal wind, and the contours are the stream function. So what we have here is that the winds here are indicating an intensification of the Bolivian high, of the circulation around the Bolivian high. And you have this westerly anomalies over the subtropics around 20 degrees south. So the presence of these westerly wind anomalies in upper levels is quite important, because that's what allows the Rossby waves propagating from the South Pacific to penetrate further inland or further into the tropics along the coast of Brazil to help form the conversion zone. And this Rossby wave is actually represented by the contours here in the stream function. So we can clearly see this disturbance coming from the South Pacific Ocean and going northward along the coast of South America and forming the conversion zone over southeastern Brazil. So these are the main ingredients in upper level. Let's see. And in lower levels, what we have is usually it's the same thing here. The arrows are showing the wind. So we have this the circulation typical from the monsoon system, with the trade winds coming into the continent over the equatorial Amazon and then turning southeastwards, forming the low-level jet. And here, the blue shades are the anomalies in the meridional wind. So these anomalies are showing a positive meridional wind anomaly over Argentina, southeast Brazil, on the location of the low-level jet. So this is indicating that actually the low-level jet is weaker there, and the moisture or the flow is usually advected towards southeastern Brazil and eastern Brazil instead of going south into the tropical South America. This circulation is mostly driven by the presence of these cyclonic anomalies in lower levels. And so this cyclonic anomaly will enforce the circulation, will help bring moisture into this region and enhance the convection and the uplift, instability and uplift and convection over the South Atlantic conversion zone. So this is typically how it looks like in general. Let's see if I said everything here. Cool. If something is not clear, feel free to interrupt and ask questions. So we mentioned about how these conversion zones are formed, and what are the main ingredients, but also other questions that arises are kind of like, why is it a diagonal? And also why, when we look what happens after the conversion zone, it's kind of like you don't have any precipitation after that. So this image on the right is actually OLR, and we can see the location of all this diagonal conversion zones over the southern hemisphere. And usually what we see is that east of that, you have these regions with no OLR, no precipitation over the Eastern Pacific Ocean and over the tropical South Atlantic Ocean. So Trenberth in 1976 first noticed that, and he said that the South Pacific conversion zone would act as a graveyard of Rossby wave activities, so inhibiting precipitation after the conversion zone. And so this raises the questions of like why we have this conversion zones being diagonal and penetrating into the subtropics. Why the Rossby waves that form this conversion zone have this curvature towards the equator when they reach the region of the conversion zone, as we saw over South America. And why sometimes this Rossby waves, they stop over the continent and form this graveyard to the east. So usually when we see on the South Atlantic conversion zone, we have this Rossby wave propagating. And when they reach southeastern Brazil, they stop there. The cloud bands and the conversion zone stays there for 3, 4, 5 days. And afterwards, this wave dissipates and then the rainfall doesn't keep on propagating toward the tropics. And this is all related to the way that the extratropics is, the extratropical dynamic over the region. So first, the diagonality of these cloud bands. As I mentioned before, the cloud band, they depend on the fact that you have this Rossby wave propagating to the subtropics. And these Rossby waves are formed by these areas of cyclonic and anticyclonic vorticity. And as these Rossby waves propagate over the subtropical jet and the polar jet over South Pacific, they tend to be elongated and tilted by the shear on the margin of the subtropical jet. And as these waves approach the continent, they go tropicalward. And as they reach regions of higher planetary vorticity over the subtropics, you start having this advection of vorticity east of the, start having uplift east of the vorticity, the cyclonic vorticity regions, forming this precipitation regions over the tropics. So usually the cloud bands will form parallel to these elongated areas of vorticity over the subtropics. And most of the times, but not always, the structure of this Rossby wave will be barotropic, especially on the extratropics. Sometimes when it reaches the tropics, it will get a baroclinic characteristics, but most of the times they will be barotropic. So this is sort of first we understand why this is diagonal, right? So why this Rossby waves or vorticity regions, they seem to be this elongated and deflected, right, to the north. The second thing that is quite interesting about the formation of these cloud bands over the west part or the east part of the continent is related to the fact that the OLR, usually the OLR anomalies remain stationary over these regions. So that's why the conversion zone would stall over these regions. So this graphic on the left-hand side is a Hove-Miller graphic. So time is on the x-axis going down. And here on the, time is on the y-axis going down. And on the x-axis, you have the longitudes. The contours, the red contours is the negative zonal stretching deformation. I'll explain this in a minute. And the blue shades is the OLR. So what we see here is that the OLR is always forming where we have more of this stretching deformation. So this term, the zonal stretching deformation, is actually the derivative of the zonal wind in the x direction. And it measures when the zonal winds are decelerating. When this term is negative, it means that your zonal wind is reducing its speed. And if you think over the South America continent, for example, what we have during a conversion zone is the trough in the subtropical jet. And close to the southeast coast of Brazil, this trough will produce this area of negative stretching, zonal stretching deformation, because of the reduced in the zonal wind speed over there. And these regions, they tend to stall the propagation of your conversion zone. So this helps stagnate the Rossby wave over that area and accumulate the energy of the Rossby wave there, making the South Atlantic conversion zone and also the South Pacific conversion zone have this characteristic of staying for a few days and causing a lot of precipitation. So the fact that the Rossby, the energy is accumulated there, it amplifies the vertical circulation and amplifies the instability and the convection. So breaking down a little bit more, I'm not going to go into a lot in the vorticity conservation equation, but just to explain why we have this uplift east of the cyclonic vorticity anomalies and the convection happening, and how all this convection interacts with its own environment and makes the cloud band or the South Atlantic conversion zone stationary. So this is the vorticity equation. It's formed of different terms. And in the case of the conversion zones, I will only highlight these three terms. So the vorticity tendency, the horizontal advection of the vorticity, of the relative vorticity by the winds, and the vortex stretching that happens when your cyclone is traversing this flow. And this is represented in these three maps. So this is a study by Van der Wiel in 2015. It's quite interesting. This is where we understand, this is one of the first studies that try to explain why this diagonal conversion zones are diagonal and why they stall over the continent. So on the left-hand side, we have the vorticity tendency as the contours, and the shades is the vorticity anomalies. So the shades are showing the positive. I didn't put it here, but you have like the cyclonic and anticyclonic circulations here, or cyclonic and anticyclonic vorticity anomalies over the map, and then the tendency of these centers to propagate northeastward over the continent here, over South America. And this term is produced mostly by the relative vorticity advection, so the advection by the circulation over the region. And notice that it's always in quadrature with the wave pattern. So that means that the vorticity or the winds caused by the cyclonic anomalies are being advect this vorticity and kind of like propagates the Rossby wave as it propagates the disturbance as the Rossby wave propagates along the coast. And you also have this term of vortex stretching, counterbalancing this. So the horizontal advection of relative vorticity is what drives the movement forward, and it's partially balanced by this stretching that happens ahead of the convection or ahead of the cyclonic circulation. So ahead of this, you're going to have uplift, and this uplift will stretch your column negative, or it will counterbalance the vorticity there. So the interaction between these two terms is what determines if this Rossby wave will keep on propagating or if it will stall. So when this anomalies reach the regions where you have accumulated energy because of the negative zone of stretching the formation, your uplift will be stronger. And this uplift will increase your vortex stretching term to the point that it might completely counteract the advection of this vorticity. And this will make your wave stall over southeastern Brazil, for example, and then dissipate. So summarizing kind of like all we've said so far, we can think of the conversion zone forming because of aspects on the basic state and on synoptic scales. So first on the basic state on the left-hand side, what we have usually is the fact that you have your subtropical jets a little bit to the north, a little bit to the north, or forming this trough over southeastern Brazil, which increases the westerly winds in upper level. And these westerly winds will open the door for your Rossby wave to propagate further into the tropics. So that's what's represented here by the blue shades in the subtropical jet, and this wiggly line, the green line, forming this Rossby wave propagating and stalling over southeastern Brazil. So in the synoptic scale, you have this wave propagating and reaching certain areas with high vorticity and the background vorticity. And then you have all this interplay between the advection of horizontal advection of vorticity by the local winds, and then the convection and uplift forming or the uplift forming the convection, stabilizing the atmosphere, forming the cloud bands, and this upward movement will cause upward divergence or divergence in upper levels and subsidence, especially to the southwest of the conversion zone. And this is why when we have the conversion zone over South America, we have a lot of convection over Brazil and subsidence over subtropical South America. So dry weather over Argentina and Uruguay, and sometimes in Paraguay. And if this convection and uplift is strong enough, it will counteract the horizontal advection of vorticity and will stall the propagation of this Rossby wave. So this Rossby wave will be trapped over this region, over eastern Brazil, and eventually will dissipate. This enhanced convection can also trigger another Rossby wave. It can also be a Rossby wave source. And we'll talk this a little bit more later. So now switching gears a little bit. So this all we saw so far was like the dynamic aspects for the formation of the cloud band and the diagonality of these cloud bands. But also there's a lot of interplay between the surface, especially the ocean surface over the South Atlantic Ocean, and the maintenance of this convection. So for this convection to be strong enough and cause precipitation and eventually stops the propagation of the Rossby wave, you need to have moisture, sources of moisture to sustain this uplift. So as we saw before, a lot of this moisture comes from the Amazon, but also a lot of these interactions comes from the Atlantic Ocean. So previous studies have identified that if you have a blocking over the Atlantic Ocean, you have a decrease in the frequency of cloud bands or South Atlantic conversion zones. And there's also evidence that positive anomalies over the South Atlantic Ocean tends to weaken the South Atlantic conversion zone, which sort of seems a little bit counterintuitive. On the other hand, numerical experiments show the opposite, that warm waters would intensify the precipitation over the conversion zone. So it's not very clear what's the role between the interaction and between the sea surface temperature in the South Atlantic Ocean and the maintenance of the South Atlantic conversion zone. But there are a few mechanisms that try to explain this. So in one hand, you have this thermodynamic mechanism described by Chavez and Nobre and also Almeida, where you have the convection over the ocean increasing the amount of clouds that is over the region that produces the solar radiation and cools the ocean surface temperature, and that will inhibit your convection. So one of the reasons why the South Atlantic conversion zone would die would be because of this reduction in the convection over the conversion zone. And on the other hand, you also have dynamic mechanisms where the cloudiness will affect the local cyclonic vorticity anomalies, producing Ekman pumping in the ocean. So this cyclonic vorticity anomalies will favor the advection of cold water into the ocean surface, so favor the upwelling on the surface and weaken the cyclonic anomalies. And recently, Pezzi et al. Published 2 papers where they disentangle this relationship, and actually they identify the role of the ocean surface as being a combination of these 2 dynamic and thermodynamic mechanisms, but mostly related to the fact that you have reduction in the ocean currents causing this upwelling and weakening the cyclonic anomalies, helping to dissipate the South Atlantic conversion zone. Cool. I need to drink some water. Anyone can have any questions? Any comments? Now I'm gonna move on into the second topic of the class, where I'm gonna talk a little bit about identification. So we talked a lot about how these conversion zones are formed. I mentioned some different studies, but how do these studies identify these conversion zones in first place and then analyze all that we've seen? So usually we can divide the methods of identification into different types. The first one would be using statistical tools like empirical orthogonal function, principal component analysis, single value decomposition. A second one will be looking, an example of the first one is this map on the left-hand side that shows the dipole in related to the South Atlantic convergence zone. A second method that is very common is defining areas of study or location-based anomalies, that is what I'm calling. So you define areas of study, identify anomalies in your precipitation, your wind, or stuff like that. And based on that, you identify events, so dates when these anomalies occurred. And this is an example, for example, the map on the middle from MarciaZilli and Mode 2017, where they identified the conversion zone based on this blue square here. I'm going to talk a little bit more about it. And the third one is more based on like what we call like object-based identification, where you define a certain number of criteria, and when these criteria are met and form a physical object on space, you consider that as a conversion zone or a cloud band. So the first example over South America is by Carvalho et al. In 2004, and one of the first methodologies to identify these cloud band objects. And more recently, a study that we developed here of using an automatic algorithm to identify these cloud bands. So the first method, the composition using statistical tools. Usually for that, we use things like empirical orthogonal functions and rotated empirical orthogonal functions. Sometimes are referred to as principal component analysis. That can be done using one single variable, precipitation, OLR, or a combination of them. Or you can also use things called single value decomposition, where you access the covariability between two different variables, so precipitation and sea surface temperature, for example. These methods are super powerful because they filter your time series, they filter your data, and identify the modes of variability that you want. You can combine them with different filters, for example, so you can filter your precipitation using 30 to 90 days filters, for example. So you will only focus on your interseasonal variability and then apply this statistical analysis and filter just the mode that you want. So they are very helpful in identifying these events, especially if you're interested in studying interseasonal and interannual variability. They are quite flexible in the sense that you can add a lot of variables to that. And they are quite easy to apply using different Python libraries, for example, or different other computational languages also would have their own packages to calculate this EOF analysis or PCAs or SVDs. And usually the computational cost of calculating that is quite low if you don't have a very large data set, of course. The downside of these methods is that it's a statistical approach and it filters out part of your variability. So you're just going to use about 30 to 40, 50% of the variability that you have, depending on how you identify it. It's what we call the fixed spatial location. So it will identify events that happen on a specific area, and it's quite sensitive to if your conversion zone happens to the north or to the south. It will be very sensitive to that. And it's quite hard to identify individual events. So it's quite hard to identify. You can say the date when the conversion zone happened, but you cannot identify spatially what's exactly the contour of that conversion zone, for example. So this is a few examples of that. On the top right, we have a graphic from Gonzalez and Vera, 2014, where they used empirical orthogonal function over the entire South America using two different filters. So they filtered the precipitation using the 30 to 90 days. So the map on the left uses 30 to 90 days. And the one on the right is using 10 to 30 days. So you're looking at two different frequencies within the interseasonal variability and how the conversion zone behaves there. We can the maps on the left-hand side is similar, but instead of using just precipitation, it's using a number of variables. So it's using precipitation, zonal and meridional wind in lower levels, air temperature in lower levels, and specific humidity in lower levels. So with that, we can have a bigger picture of how the conversion zone happens over South America. And then the map on the bottom right is showing an example of the single value decomposition. So here it's relating the OLR over the continent, so represented by the shades here on the map on the left, to anomalies in sea surface temperature over the South Atlantic Ocean. So this method is quite helpful when we want to understand, for example, how the sea surface temperature anomalies on the Atlantic can influence the location and the intensity of the South Atlantic conversion zone, or vice versa, how the South Atlantic conversion zone can affect the sea surface temperature there. So this methodology will give like the covariability between these two variables. Cool. The second method that I mentioned is what we call a location-based identification. So it's quite nice when you want to understand what's happening over a specific area. So it's a targeted analysis, and it's useful to understand, for example, intense conversion zones causing natural disasters over a specific part of the country. It's very flexible in the sense that you can use whatever variable you want, and it's quite straightforward. Your definitions is straightforward to apply, and it doesn't have a lot of computational costs. The downside is that it's subjective. Usually the threshold is determined by the researcher. You can use the percentiles to determine the threshold, but ultimately it's based on the fact of where you chose your threshold, your area, and the time of the year that you are interested. It's also fixed in space, so since you're just concerned with one specific area, it's going to be fixed on space. It doesn't look at what happens in general with all the cloud bands or all the conversion zones that are happening there. And usually it's hard to say that that's a South Atlantic conversion zone. It's more an inference-based attribution. So you look at the anomalies in precipitation, the anomalies in circulation, and say like, yes, these anomalies look like a conversion zone, so I'm going to consider that as a conversion zone. So a few examples of this is, for example, Irat and Green, that were interested in extreme precipitation over different areas of South America, and how different intraseasonal variability modes might affect that. And also Mattingly and Mote that I mentioned before, where they identified as South Atlantic conversion zones the days where you have precipitation above a certain threshold over the blue squares here over South America and the South Atlantic Ocean. In this study, they differentiate between continental South Atlantic conversion zones, so days where only your anomalies were only present over the continent but not over the ocean, oceanic South Atlantic conversion zones, the other way around, or a combined, so when both areas were classified as having above average precipitation, whatever criteria they defined there. And the third method that is also very used is the object-based identification. So this one, instead of looking at statistical analysis or statistical variables, it's more based on how we visually identify a cloud band. So if we take a satellite image, for example, this one on the right, we see this area of lower OLR, and we see that it's a diagonal thing that goes from, the tropics to the exotropics, and try to define computational criteria to identify this object. So one of the first times that this was used over South America was in this paper from Carvalho et al., 2002, where they developed this algorithm called Mascote. So first they define a set of criteria to identify areas of contiguous OLR below a certain threshold. If I remember correctly, it's 200 watts per square meter. And then they calculate the fraction of this of below threshold OLR over different regions here defined on the map, and have a certain statistical analysis for this objects identified. And this is classified as South Atlantic conversion zone. And on top of that, they used also a EOF analysis to identify the main criteria and the events that will be considered continental versus oceanic. So when the cloud bands are located mostly over the continent than over the ocean, and also strong versus weak South Atlantic conversion zones, for example. So the advantages of this technique is that it allows you to identify specific objects in space and time. And you can track these objects in space and time. And it's also quite flexible to include a number of characteristics. The problem is that it relies on subjective thresholds also, and can be computationally very expensive. Nathan is asking me if I have ever investigated correlation of South Atlantic conversion zones with the South Atlantic dipole variability. I personally haven't. There are a number of studies that talk about that, and I will mention this a little bit later on the presentation. So I will hold a little bit, and we will talk about that later. Is that okay? So another method for identifying these objects is the one that I'm showing on the right-hand side. It's called the MatBot. So this is part of my research here. So I'm going to use a little bit of the time to explain that. So let me go back here. So the MatBot actually identified these areas of contiguous or continuous low OLR over the continent, and uses certain criteria like diagonality and the location of that over the continent to identify these individual events. So with that, what we have is dates where the cloud band occurred, and also the physical shape of that. So in this image, the contour, the pink contour, is showing this physical space that this cloud band envelope, or the South Atlantic conversion zone envelope, is occurring over space and time. And then we can aggregate subsequent dates to form the South Atlantic conversion zone. So when you have 3 or more or 4 days where this cloud band occur in sequence and occurring more or less over the same area of the country, we can say that that's a South Atlantic conversion zone lasting, like, for example, 4 days or so. And as I mentioned before, one of the downsides of this methodology is that the threshold that we use to define a cloud band is subjective. We can try to compare this with observational techniques and see if we can get most of the events, but it tends to be quite complicated. And it can be quite computational intensive, especially if you are using a lot of very high resolution satellite image. So as I mentioned before, this is part of my research here. So this is a database that we produced a few years ago, identifying all cloud band events over South America since 1979 to 2018. It can be accessed by that QR code on the right-hand side if you want to take a look. So this is an example of how we can use these objects by kind of just streaming the precipitation that happens within that cloud band. So on this website, if you go there now, you're going to land on a page looking like this, where it shows where most of the cloud bands occur in the climatology over Brazil. And you can also flick over, there's a button here on the bottom left where you can see the anomalies in during El Niño and La Niña years, for example. If you click here on the top, if you click on all cloud band events, you're going to have a map like this, or a page like this, a graphic like this, where here what we have is each year from, you cannot see it on this image, but it goes from October to April. So the x-axis here is every day from October to April, and the y-axis is every year, all the years between 1979 and 2018. And these blue shades are days with a cloud band. So not all cloud bands will be a conversion zone. Only when they last longer, there will be a conversion zone. But cloud bands can also be identified like cold fronts and more transient events. So these blue shades are all the cloud bands that you have between between October and April. And then the colored dots that you have around there are days where we have a natural disaster occurring. So there's a list of natural disasters here on the left-hand side, and these dots are the dates. You can go here and select one year, like the green box here. And when you select the year, you can see the time series. Why is it not going? Oh, there you go. You can see the precipitation time series, and again, this blue shade indicating where we had a conversion zone or a cloud band event on that year, and also the the location, like the dates with natural disasters. And then selecting one of these blue boxes, clicking on that, you're going to go to the first image that we saw before, where you have the cloud band over the continent. On the bottom here, you have all the dates of that specific event. So you can flicker through different dates and see how the precipitation was in the day, and also where you have this natural disaster events. So if you're interested, you can scan this QR code and check the page there. Okay. And on the National Weather Forecast System in Brazil, they also have a methodology to identify the conversion zones. So they use a list of criteria to define if the presence of convergence in lower level and this massive cloud bands are a South Atlantic conversion zone or not. And usually they classify this in different types. So the circulation that forms these conversion zones can change a little bit from event to event. And that also influences the location of the South Atlantic conversion zone over the country and intensity that it happens. So one of the first type of South Atlantic conversion zone is what they call a blocking anticyclone. So this is characterized by a stationary or slow-moving cold front with this post-cold frontal anticyclone forming over the Atlantic. So you have this high circulation system over South Atlantic Ocean. It has a barotropic structure. So if you look, the image on the left is in lower levels. The image on the right is in upper levels. And this anticyclone are collocated in both regions. And you also have, in upper level, you can see this frontal structure forming. It's ahead of the anticyclone here. So it's forming over the South Atlantic Ocean and kind of like protruding towards southeastern Brazil. And that's where the conversion zone is formed. Yeah, it usually can propagate in land, so it will cause sort of like continental scale cloud band or conversion zones there. A second type is like a more traditional cold front structure, where you have the cyclonic circulation further into the South Atlantic Ocean. This structure is a little bit more baroclinic, and the conversion zone is formed by the frontal wave activity related to the cyclonic, the propagation of the cyclonic anomalies. So this is kind of like the extratropical or the extratropical disturbances are what provides the energy and the convergence to form the envelope of the conversion zone there. It transports a lot of moisture from the Amazon into the continent and into the coast of Brazil in this case. And the third type is what we call cutoff flow. So when this extratropical disturbance is strong enough, the cyclonic anomalies can get detached from the structure of the subtropical jet and form a closed circulation off the coast of South America. And that will provide the input, the energy necessary to form this conversion zone. It usually, because of the structure of this cutoff flow with a lot of like lower temperatures in the upper levels and higher temperatures on the surface, it will increase the instability and form these conversion zones over eastern Brazil or southeastern Brazil, and then tend to be very, very intense on these cases. Nice. And now I would talk a little bit more about variability, trends, and future scenarios. And I will then mention also the relationship with the South Atlantic dipole that Nata asked. And this is also a good example of how different ways of identifying the cloud band or the conversion zone can help us study it and understand the dynamics and the mechanisms that form them. So in the literature, we usually can see the cloud bands or the signature of the South Atlantic conversion zone in different scales. So on the left-hand side is one of the first, a very classic study from August Spiegel and Moe from 1997, where they use a rotated EOF. Here's this is the fifth mode of the rotated EOF because of kind of it looks at a very large area over South America and the Eastern Pacific Ocean and North America also. So usually the way the methodology works, it will end up having this on a very high mode. But here what they did is to filter the OLR precipitation using a 10 to 90 days to retain only oscillations with in the OLR field with 10 to 90 days period after removing annual and semi-annual cycles. And then what we're going to have is this positive area over South America and a negative area over Southeast and South America. In interannual scales, this is used, this is a rotated EOF for December, January, and February of observed precipitation anomalies. So just the long-term mean removed, no filter, nothing. And this is the signature that we have over Eastern Brazil and Southeastern South America. This is done using precipitation from weather stations. And the third one is an interdecadal variability. So here, instead of filtering low or high frequency anomalies, what the authors did was to filter just the low frequency anomalies. So that is done using a 9-point Gaussian moving average filter. So with that, we remove everything below annual scale. So first you average the precipitation over the DAF, one value per year, and then you use this moving average to remove oscillations below 8 years and just retain this decadal variability. And again, what we see is this positive areas over Eastern Brazil and negative, an opposite area over Southeastern South America. So that's sort of recurrent in all scales where you have this dipolar structure. And that's the dipolar structure of the South Atlantic conversion zone over Eastern Brazil and Southeastern South America. Usually when the South Atlantic conversion zone is active, it will cause negative OLR, positive precipitation, and all of this over Eastern Brazil, and dry weather over Southeastern South America. But when it's inactive, the opposite will occur. You're going to have enhanced precipitation over Southeastern South America and dry weather over Brazil, or dry climate over Brazil. So this is how the circulation looks like. So just repeating a little bit all those ingredients that we mentioned before. The top map is showing the active South Atlantic conversion zone with the cyclonic circulation over the ocean. Sorry, this is an anticyclonic circulation. The cyclonic circulation over the continent, the anticyclonic circulation over the ocean. The cyclonic circulation is what is helping with the conversions of moisture over Eastern Brazil. It's also affecting vorticity, causing the convection over the coast, and increased precipitation, and in this case, reduced OLR in the blue shades over Eastern Brazil. And then you have the opposite signal over Southeastern South America with subsidence, increased OLR, and reduced precipitation over Southeastern South America. In this case, the wind anomalies here represented by the arrows are indicating this weakening of the low-level jet, and then the low-level jet weakened over the subtropics, and it actually affects, you have more like an easterly transport of moisture from the Amazon into the east coast of Brazil. During an inactive South Atlantic conversion zone, the figure on the bottom, what we have is more like an anticyclone over the country, over the continent, and a cyclone over the subtropical South Atlantic Ocean. So this anticyclone will actually enhance the low-level jets and help bring the moisture from the Amazon into the subtropical South America, so into Argentina, South Brazil, Uruguay, and cause precipitation there. This precipitation will also cause upper-level divergence and subsidence, compensatory subsidence to the north of the South Atlantic conversion zone, or to the north of the convection. In this case, it's an inactive South Atlantic conversion zone. And the subsidence will occur over Eastern Brazil and inhibits the precipitation there. Also, the circulation will bring this drier, more stable air from the Atlantic Ocean into the region, further inhibiting the convection there. So I mentioned before that we can look at this activity of the South Atlantic conversion zone in different scales or different variabilities. So just breaking down a little bit what triggers or what drives these different scales. Here on the left-hand side, we have the study from Gonzalez Evera, where they first filtered the precipitation anomaly, filtered the precipitation time series using 10 to 30 days filter and applied an EOF analysis for that. I think this is a rotated one. And what we see here is this dipole, again, over eastern Brazil and southeastern South America. In this high frequency intraseasonal variability scale, so up to 30 days, what we have is that the southern part of this dipole, so the dipole over the part over southeastern South America, is stronger or more intense than the part of the tropics. And this is mostly related to the fact that this variability is more related to the propagation of the Rossby waves, or it's highly triggered by the propagation of the Rossby waves in intraseasonal scales, usually triggered by the South Pacific conversion zone convection. So it has more influence in causing precipitation over one of the two dipoles, but usually when it causes precipitation over southeastern South America, so during an inactive South Atlantic conversion zone, the precipitation can be quite strong there. This maps here on the right is showing the mechanisms related to this propagation of the Rossby wave. This is a model using a linear barotropic model forced by convection over the South Pacific conversion zone. And this barotropic model will trigger, or this convection will trigger this Rossby wave propagating across South Pacific Ocean. And when it reaches these regions of the east coast of South America, will trigger vertical motion, so upward lifting and convection over the continental area. This is the vertical profile of this circulation over the country, over this this latitudinal band. So usually on interest in this very high frequency intraseasonal variability is usually driven mostly by this Rossby waves propagating over the extratropics. If we look a little bit further or into the variability spectrum, if we can say that, so instead of filtering the very high frequency, we filter still in the interseasonal frequency, but we filter the precipitation between 30 and 90 days. This is the dipole you're going to have. So in this case, the tropical part of the dipole is a little stronger than the extratropics. And looking at patterns of teleconnections globally, this is strongly related to the MJO. So these maps here are showing two different phases of the MJO. So these maps are showing composites of OLR during the different phases of this dipole on the left-hand side. And what we see is that when you have suppressed convection over eastern Brazil and enhanced convection over southeastern South America, so when you have an inactive South Atlantic conversion zone, what we have over the Indian and Pacific Ocean is increased convection over the maritime continent and suppressed convection over the Pacific. So this is typical of a Madden-Julian oscillation phase 4 and 5 that will reduce the precipitation over Brazil, but increase over southeastern South America. And if you look at the opposite phases, so phases 8 and 1, or when the South Atlantic conversion zone is active, you have this enhanced convection over eastern Brazil and suppressed convection over southeastern South America. And the opposite, comparing this with the other phase, with the top phase, the convection over the maritime continent and the Pacific is the opposite. So you have suppressed convection over the maritime continent and enhanced convection over the Pacific. So kind of like indicating this influence of the Madden-Julian oscillation. So when we look at this intraseasonal scale, then considering everything from 10 to 90 days, what we have is that you have this slower moving 30 to 90 days Madden-Julian oscillation related anomalies or envelope, suppressing or enhancing the convection over Brazil, or modulating the phase of the South Atlantic conversion zone over Brazil, over the entire South America. And at the same time, on this more fast-moving intraseasonal oscillations, you have the Rossby waves influencing the way these Rossby waves will propagate towards South America. And then it's the combination of these two phases that can cause the very intense conversion zone. So when both the 30 to 90 days variability and the 10 to 30 days variability are in phase over the continent, you can have very strong convection and precipitation either over southeastern South America, if it's an inactive South Atlantic conversion zone, or over eastern Brazil, if it's an active conversion zone. The Madden-Julian oscillation is out, and all of this is also can be a little bit affected by the southern annular mode, and also by El Nino. So there are a number of literatures indicating how this the combination of, for example, El Nino and Madden-Julian can affect the South Atlantic conversion zone in Brazil. And talking about El Nino, we move to interannual variability. And when we look at this main mode of variability in interannual scales and correlate this with the sea surface temperature, we don't actually see a lot of things over over the Pacific Ocean. So we do see anomalies there, but these anomalies are not very characteristic of El Nino. But we do see a lot of anomalies over the South Atlantic Ocean. This is for December, January, and February. But if we look at what happens over spring, so doing the same analysis in interannual scales, but looking at the spring mode, which also has this South Atlantic, this dipole, we see more clearly this influence of the tropical Pacific Ocean in the form of kind of like this typical quadrupole wave over the Pacific that is related to the El Nino. And then this Rossby wave propagating across the South Pacific into South America. So in interannual variability, in interannual scales, El Nino has a strong influence in the signal of the South Atlantic conversion zone in spring. And in the summer, the signal is not that strong, and it's usually mediated or modulated by the Madden-Julian oscillation. And one more cool thing that we found over when we are looking at the interannual variability is that if you compare the signal between spring and summer, is that they have opposite signals. So looking at this EOF, we have in the spring, when you have positive anomalies over eastern Brazil, you're going to have negative anomalies over eastern Brazil in the summer, and the opposite over southeastern South America. So these two modes, they are strongly correlated and positively correlated. And if we get, for example, the precipitation over this box in eastern Brazil and see what happens over the year. So the black line is the climatology. So considering all the years in this, all the years, precipitation over all the years in this box, and how it advances from September through March. So peaking here in December and January. And the dark shaded line here, the darker dashed line, is considering only years where the spring dipole is strong. So years where you have enhanced precipitation over the north part of the dipole in spring. That's what we have in the dark shaded here. You have increased precipitation in the spring, and then the precipitation in the summer is a little below the average. And if we do the same thing for the summer, so here considering the positive mode, so when precipitation is lower in the summer in eastern Brazil and higher in southeastern South America, what we see is that you definitely have that anomaly, negative anomaly in the summer, and you also have a positive anomaly in the spring. So it seems like the dipole has also this interseasonal connection where the conditions during spring can determine what's going to happen in the next summer by flipping this dipole. So if you look at this article from Green et al. In 2007, there are the explanations of this mechanism, but most of that is related to the fact that if you have above average precipitation during spring in eastern Brazil, that would cause anomalies, soil moisture anomalies that will change the local circulation and inhibit the formation of these cyclonic anomalies necessary to form the conversion zone in the summer. So this is quite interesting that it happens. You see this in the interannual scales. And also in interannual scale, we have this influence. I mentioned the influence of the South Atlantic Ocean, and Nata also asked. So one of the characteristics of the interannual variability is having this connection with this dipolar mode of sea surface temperature over Atlantic Ocean. So that's the South Atlantic dipole. Usually, here in this case, we are using, they are calling this the negative phase of the South Atlantic dipole. And this is characterized by negative anomalies of sea surface temperature over the tropics and positive anomalies over the subtropics. And what happens is that this positive sea surface temperature anomalies, they sustain the establishment of these anticyclonic anomalies over the South Atlantic Ocean. And that forces the cyclonic anomalies or the Rossby waves to propagate over the continent and establish over the continent, forming the South Atlantic conversion zone here. So this is sort of similar to the blocking South Atlantic conversion zone that we saw before, and some other maps that we saw before, where the cyclonic anomalies stays on top of the continent and favors this easterly transport of moisture into the, westerly transport of moisture from the Amazon into eastern Brazil, feeding the conversion zone and increasing the precipitation over the continent. When you have the opposite signal, so when you have negative sea surface temperatures over the tropics, this pattern is flipped, and that will inhibit. So if you have positive sea surface temperature over the tropics, you're gonna have you're gonna inhibit the formation of the South Atlantic conversion zone there. I hope this answers your question, Nata. Also, you can check this paper from Bombardi et al. 2014, where they explain the mechanisms a little bit better. Cool. And finally, in interdecadal scales, we again see the same thing of the dipolar structure over the continent. And also we have this flip in signal between spring and summer. So the drier springs related to wetter summers and vice versa. Over eastern Brazil, this pattern is also seen in interdecadal variability scales. In this case, this dipolar pattern is related to opposite sea surface temperature anomalies over the Pacific, and there is some relationship with AMO, IPO, and PDO. So a lot of times, it's quite hard to define what is happening actually in this decadal scales because our time series are not long enough. So it's still not very clear what patterns are actually driving that, but it's important to keep in mind that this dipolar pattern do have some decadal variability. And if we are doing trend analysis, for example, we always need to take care of being actually identifying trends and not just the phase of this decadal oscillations. So, and that's why I'm saying that. If we check the EOF here, these authors, they got the precipitation data over South America and did a statistical analysis called the trended EOF, where it's like finding the main component or a EOF pattern, but looking at trends in the precipitation and not the actual precipitation. And when you look at, or when you do any sort of composite or trend analysis over precipitation over South America, what you're going to see is again this dipolar pattern where you have reduced precipitation over the tropics and increased precipitation over the extratropics. And this does look a lot like the dipolar pattern that we saw in the decadal analysis. So a part of this, in this study, they analyzed the influence of ENSO and decadal variability related to ENSO onto this dipole, and they find that part of this trend that we see in recent years is due to the decadal variability, but part is also due to climate change. And the fact that you have a reduction in precipitation over the tropics suggests that this pattern is also indicating some influence of the South Atlantic convergence zone, and more specifically, a reduction in the frequency of this convergence zone, or active phase of this convergence zone. And this paper this is from my PhD. So here in this paper of 2019, I analyzed the same thing, these changes in precipitation from 1979 to 2014. So the shades here is indicating the trends that we have in this precipitation. So again, this dipolar pattern. Here, this changes, the trends are not so significant, or they didn't pass the significance test, but you still see the pattern quite clearly over the continent. And the contours here are indicating the average precipitation, the limit to the South Atlantic convergence zone loosely, over South America in 3 different decades. So the red ones is up until 1991. The browns are in 1992 to 2004, so it's a little hard to see because it's quite close to the reds. And the black is in more recent years. And this is removing strong ENSO years. And what we see is this kind of like pattern of the South Atlantic convergence zone shifting southwestward over the continent. And this is the mechanisms that we identified as being related to this southwestward shift of the convergence zone, where you have the South Atlantic subtropical high expand over the continent, towards the continent, and that affects the circulation over the northern boundary of this conversion of the subtropical high, which will reduce the northerlies. So if we remember there at the beginning of the class, the northerlies over around the west boundary of the subtropical highs is one of the main ingredients to form this convergence zone. So if you weaken this northerly wind on the northern boundary of the convergence zone, you're going to also weaken the convergence here over kind of like more tropical latitudes. On the other hand, what we saw is sort of like an enhancement of the moisture transport towards South Brazil, so towards the southern margin of the convergence zone, forming sort of like this dipole with reduced precipitation over the tropical part and increased precipitation over the subtropical part. And that suggests that this entire envelope of the South Atlantic convergence zone has been shifting southwards in recent years. Again, this analysis is done over 30 years, so we have the risk of having the influence of decadal variability there. So what we did is first try to analyze what a set of climate models from CMIP5, how they represented the South Atlantic convergence zone, and how they represented this poleward shift of the South Atlantic convergence zone in different scenarios. So here we are using the historical scenario, so all kind of like changes in the recent years from the Industrial Revolution to present. Natural scenario, so just the natural changes in the atmosphere, so removing human anthropic influence. The greenhouse gas scenario, so only increase in CO2 due to human activity. Aerosol scenario, ozone, and land use change scenarios. So you can find these different scenarios in the CMIP5 models. And when we analyze the trends in precipitation and in the South Atlantic convergence on these modes, so looking at here, I'm looking at precipitation over southeastern Brazil on the top graphic and over southeastern South America on the bottom graphic, and try to see which of these forces are actually causing these trends in precipitation. What we see is that there's a lot of mixture there's a very low coherence between the models, so there's a very low agreement between the models, but there's an indication that maybe greenhouse gases, increases in greenhouse gases, and land use change has affected the precipitation over eastern Brazil. and over southeastern South America. So decreasing precipitation over eastern Brazil and increasing precipitation over southeastern South America. So this type of attribution studies give us a little bit more confidence that climate change due to increasing greenhouse gases can be affecting this position of the South Atlantic convergence zone and increasing precipitations over southeastern South America and causing dry weather over eastern Brazil. Diaz and Vera also had a very cool analysis along these lines, if you guys want to check a little bit more. Also, this other study is more focusing on how the circulation is changing in the future and how we can use that to identify changes in the convergence zone. So Espinosa et al. 2021, they used winds in lower level and precipitation, if I remember correctly, and identified clusters of circulation over South America. So using cluster analysis, identified different weather patterns over South America. And one cool result that they had is this weather pattern that is very common over on the dry to wet season transition, so around September, October, and November, more or less. And it's related to moisture flux and winds over eastern Brazil forming precipitation here. So it's related to the presence of the South Atlantic convergence zone. And in a study from 2023, Juana Agudelo et al. Identified that this mode is becoming less frequent in the future, in future scenarios. So this is what's represented by this graphic here. The black line is the observed precipitation caused by this this mode, or the frequency of this mode. Sorry, I don't remember exactly what is on the y-axis, but it's related to the frequency that you have this weather pattern over the region. Causing precipitation or being more active, especially October, November, and December. The blue line represents how the historical models are showing that. So you have some bias in these models, but they sort of represent the overall frequency of this mode in the historical scenario. And then in the future, you have this decrease, especially in October and November. And they identified that this actually represents a change, that this weather pattern occurs 13% of the time in the present, and then it will occur only 7% of the time in the future during this transition period into the wet season. So this suggests a reduction in the frequency of South Atlantic convergence zone in this period, so September and October especially, and also a late start of the monsoon season for this pattern. So also this is another example of how we can use different analysis to identify the convergence zone or any other weather pattern that we are interested. The same study also identified this other weather pattern related. This is more frequent in the summer, and it's related to an active convergence zone. And in the summer, this pattern will change also, will become less frequent. And we'll have like this map on the middle is showing the difference in this weather pattern identified in the present and in the future, indicating this sort of like anticyclonic anomaly, so indicating that the cyclonic anomaly necessary to form the South Atlantic convergence zone becomes weaker in the future. So that means that that represents a reduction in the frequency of these events in the peak of the rainy season. And this is related to changes on the subtropical high and affecting the convergence over the region. And this map here on the right-hand side is also showing these changes in the number of rainy days over the region in the future. So this is using regional climate models on the left and global climate models on the right, also reinforcing this idea that you are having fewer rainy days in the future in general, and also you have less frequent circulation patterns or weather patterns that lead to convergence zones in the future in the summer. So kind of like bringing this all together, these two previous studies identified that the frequency of cloud bands or South Atlantic convergence zones are becoming less frequent in the beginning of the rainy season, so in the transition period, and also in the peak of the rainy season. But they didn't say anything about how more or less intense these events are going to be in the future. Quite recently, we published something here in the environmental research letters. So this paper is here in the link, where we identified only cloud band events that are considered very strong. So cloud band events that are have very intense precipitation on that. And we identified that these events are becoming more frequent in the future. So stepping back, let's explain this. This graphic here on the left-hand side, the stripped bars are showing the frequency of all cloud band events over South America in the present day in blue and in the future in red. And these are, for here, in this event, in this case, I used different scenarios. So the first is a convection permitting model where the convection is explicitly resolved over South America using 10 years of data. And the other three are parameterized climate models. The first one is a very high resolution, 25 kilometers, and the other two have lower resolution. And in all these four simulations, what we see is a decrease in the total number of cloud band days over South America in the future. And this decrease is about 20 to 30%. So we're going to have fewer days with South Atlantic convergence zones or other types of cloud bands in the future. And this is an agreement in all the models. Then the second part of this study was to see what happens only on those events that produce a lot of precipitation. And this is what we are calling intense cloud band events. We define these intense cloud band events in different ways, but I'm going to focus on these blue bars, which are the ones that cause intense precipitation. In the present day, they occur, we consider them as occurring 20 days per year. So that's the threshold that we use. So they all have the same frequency in the present day. And we're going to see what happens with these events in the future. And in the future, what happens is that these intense precipitation events become way more frequent. So from 20 days per year in the present, they start occurring about 60 days per year, which is equivalent to a 200% increase or a 3 times increase in the number of this very intense precipitation. And also they will start contributing more with the precipitation. So instead of contributing 9% as they do in the present, they will contribute 24% of the total precipitation in the future. And here is more or less like a visual idea of what that means. So the right-hand side, this contours is the frequency of days per year where these events occur, this very intense precipitation occur, very intense cloud band events occur. And the purple is representing the 3%, so about, I think it's 10 days per year or something like that, where they occur more frequently in South America in the present day. And the right-hand side is in the future. Sorry, my battery is running down, so I'm kind of like, I'm almost finishing here. And the right-hand side is in the future. So the areas where these events occur, about 10 days per, 3% of the days of the year, they expand, and indicating this increase in the frequency of these very intense precipitation events or very intense cloud band events over the entire South America in this future scenario. And the bottom here is a graphic kind of like showing where these events will, when in the year these events will change. So the blue line is the all cloud band events, showing this decrease in the future, and especially in the beginning of the rainy season. So what we see before of kind of like the South Atlantic convergence zone being less frequent in this transition period. And the blue bars here is showing the increase in the frequency of this very intense events, especially on the peak of the rainy season. So in the peak of the rainy season, you're going to have fewer cloud bands, but when they happen, they will have very strong precipitation. There's a podcast about this paper in this link if you guys want to listen later. It's in Portuguese, I'm sorry, but I think it won't be very hard to understand for Spanish speakers. So this is my last slide, wrapping up what we kind of like a lot of what we discussed. I thought that a nice way to bring it all together is thinking about what we don't understand or what are things that we need to understand a little better. So in terms of like what is the cloud, what is the South Atlantic convergence zone, and how this helps with the onset of the monsoon season. The South Atlantic convergence zone is a some people consider that as the trigger of the monsoon season over parts of Brazil, but that mechanism is not very clear, understood yet. And also the fact that the conversion zone is related to the presence or to the occurrence of droughts and heat waves, or the absence of the conversion zone can be related to the droughts and heat waves, are also quite, it's an area that we would like to understand a little bit more. So kind of like wrapping up this last idea of future changes, what are the consequences of this decrease in the frequency of events to droughts and heat waves in the country or in the continent? In terms of how these conversion zones are formed, we have a lot of influence of the tropics and of the extratropics. We understand quite well how the convection on the Amazon can help trigger these events, and also how the presence of Rossby waves can help trigger these events. But we still need to understand a little bit more how interactions between the surface and the atmosphere can influence the occurrence and the persistence of these events, both over the continent in terms of evapotranspiration from the Amazon, for example, as over the ocean. And also the role of how this, the propagation of the extratropical Rossby waves also influence the persistence of these conversion zones over the continent is a little bit unclear. And I also mentioned in the beginning that this enhanced convection during the conversion zone can also trigger a Rossby wave. And this Rossby wave can affect the weather downstream, so can affect what happens over Southern Africa. And this is also an area that it's quite intriguing and not very well researched. In terms of identifying that, we have new techniques related to machine learning and computational vision can help improve us identify these conversion zones, and also improve these object-based techniques to better understand what happens during the conversion zone. And in terms of future projections, there's not a lot of agreement between the models, among the models, in terms of what's the signal of the change in the future, especially over the tropics. Over the subtropics, this is more clear, but in the tropics, it's not very clear. And using event-based or process-based methodologies, like understanding what happens with the weather patterns or with the South Atlantic conversion zone, can help us extract more information from these models and understand a little better our future projections. I hope I still have battery to wrap up the class. So that's what I prepared for today. I don't know if you guys have any questions or you want to comment anything. Let me stop sharing.
Marcia, thanks a lot. I'll stop the recording now. Just a second.
How is my battery? Let's try to figure out. Okay, I have 7%. I think I have a few more minutes.